now that we've got some feeling for using tangent lines as approximating functions, which shows up in all kinds of crazy places, including lots of very, very modern machine learning applications and approximation methods that just do this over and over and over again, we can actually move to something a bit more abstract. So it turns out that one of the better ways of figuring out what all this notation is about with these dy's and these dx's and this Leibniz notation is through linear approximations and linearizations. So I have a not so satisfying definition of these dy's and dx's to try to make sense of all this notation. So we're going to have some x, it's going to tell you where you are, and then you've got this dx. Okay. And dx is an independent variable. Okay. It is its own thing. It gets to be whatever it wants. And for us, what it wants to be is just delta x. So delta x might mean something to you, but it's dx. It gets to be kind of whatever change it wants to see in the world. dy is the dependent variable. It has a relationship. dy is just f prime times dx. Okay, it is, okay, dx is going to be some change. F prime is the derivative times that, which should tell you how much the y is changing. So in other words, dy is the change in a linearization. All right, so think about that for a second. X is changing by a certain amount. I multiply it by the slope, and that should tell me how much the y value of the tangent line is changing. Okay. Importantly, if I take dy and I divide by dx, I get our old friend dy dx. What does that look like? Well, it looks like f prime of x dx divided by dx. That's just f prime of x. So now this is true almost by definition, just by saying dx over dx is 1. Okay, so at its heart, it's a little bit circular, but the reason why dy dx is equal to the slope is because this is how we defined dy and dx to work. That dy is just how much a tangent line changes, how much the y value in a tangent line changes when the x value changes by a certain amount. So dy dx is by definition the slope of L of x. But that's all it's ever really been to us, is some notation, this differential. Okay, so people will talk about dx's as some infinitesimal amount of change in x and dy as some infinitesimal change in y, but you don't really need to talk about infinitesimals to have a tangent line with a slope. Okay, so this will be our definition of differentials. It's a good one. If you study lots and lots of math, you'll see many different definitions, and part of that has to do with people care about weird things like what is a differential on, or what is a derivative if your functions live on the planet Earth. So they live on a globe or a sphere instead of on a flat surface. And people then start thinking really deeply about what is a differential in these different contexts. Okay, so let's draw a picture of what's going on here. dx is just our delta x, right? It is whatever change it wants to be. This is based at some x value here. But once you say how much that dx is changing, your dy is going to be the change in the y value of the tangent line, so that their ratio is the slope. Meanwhile, there is this other thing called delta y. But delta y belongs to how much the function's changing. So in this case, our delta y is actually less than our dy, right? Because it curves down, the change in my function, this delta y, is smaller than my dy, which lives on the tangent line. Okay, got it? Let's just do one quick example of this to try to hammer it home. Let's let y equal our square root of x, just like before, and we're going to find dy when x is 100 and dx is 2. This should look familiar. So, working through this again, it looks like we have an x value that's going to be 100. We have a delta x, which is my dx, and that's going to be a 2. Okay, we have we want to know dy. So dy is equal to our y, all right, f prime at 100 times my delta x, that's a 2. So let's find that f prime, or y prime if you like, equals the square root of, not in the denominator, equals 1 over 2 square root of x. So f prime of a is equal to 1/20, just like before. So this is just 1/20 times 2 is equal to 0.1. That should look familiar. Before, our estimate was 10.1. We went from 10 to 10.1 because the change in y of my tangent line was just the 0.1. So in other words, another way of thinking about this is that we had our L of x is equal to f of a plus f prime of a times x minus a. This thing, this part is my dy, right? How much is the y changing in the tangent line? That's it. So dy is equal to f prime of a times x minus a. All right. It's an approximation for the change in the y value. That's it. We could go much further, and depending on where you're looking in your book, we could talk about bounding the errors and saying, okay, this dy is not quite delta y, but how far off is it? Can we create some bound in how far off we go? And this is a great question. And people who get really good at both estimating and bounding their errors, they get paid good monies by a lot of different companies doing things like optimization, amongst other things. So it's a really good question to ask. We're not going to go into it right now, but I encourage you to. If you think that's interesting, go for it. If you think differentials are interesting, keep reading up on those, because that is its own very abstract, very interesting field in math and calculus, and people have put a lot of thought into what are good ways of defining differentials, and not all of them agree. So I hope that was enjoyable and educational, and you will now use it in your day-to-day life to make the world a better place.